Okay, last I left off, I believe we were talking about chemical change, or did we go further than that? Chemical. We talked about surface area. Okay, that was on Monday, right? Yeah, last week during lecture time. You don't remember? Anyone remember? I can just make it up. Let's do that. I'll just make it up because I believe we were talking about how balancing chemical equations. Yes, so this is the part that we stopped. Good, good. Okay, so we're going to go through and do a recheck of our balancing of chemical equations to kind of make sure we have good understanding, because that is going to be your foundation of a lot of your chemistry. So last we left off, we were talking about balancing chemical equations. So let's see. Let's say we have okay, so let's say we have this chemical equation, and our goal is to balance it out. Try to make sure that we got it. Okay. So what was the first thing that we did when we started balancing chemical equations? Guys remember? Write down the chemicals. Okay, so we're going to go ahead and write down the chemicals. So we have sodium, we have phosphorus, we have oxygen, we have manganese, we have nitrogen. Okay, and I'm going to show you two ways of going about this. One is the longer way, and then one is the shorter way. Okay, so yes, ma'am. After the very first one, HQ. So if you guys remember, S stands for what? L stands for G stands for, and AQ stands for aqueous. Okay, so which side is our reactant side? Which side is our product side? Okay, so we know our reactant side and our product side. On our reactant side, how many sodiums do we have? So as we remember, this here is called the what? That lower number right here is called the what? There we go, the subscript. So we know that this guy is called the subscript. And we know the number that we're going to be putting in front is going to be called coefficient. Okay, so the subscripts helps us understand the chemical formula. That can't change. So that has to always be the same. So you got to make sure that you have the right subscripts. Otherwise, your balanced chemical equation is going to be wrong. Okay, but the coefficient we can actually change. So we can't change this. This is set in stone, based upon our chemical formula. Okay, but our coefficient we can change to balance out the chemical equation. Okay, so then how many sodiums do we have? You were telling me earlier. 3. How many phosphates? How many phosphorus? 1. How many oxygens? And we're going to multiply 4 times, because you're saying that subscript that's outside of that is multiplying the entire thing. And you have 4 copies, right? That's what it's telling us. Okay, so we have a total of 16. But we have 4 here, and then we have 4 times 3, and that's 12, right? So all together, 16. You guys see it? Don't see it? Okay, there's an oxygen here, right? Okay, since there's an oxygen here, it has 3 around it normal. Since this guy's in parentheses, we have to multiply 4 times this, and we're also multiplying 4 times that. Because what we're saying is that we have 4 copies of it, right? We have 4 copies. This ion is called nitrate. Okay, and nitrate is a polyatomic ion, and you guys have a table. Okay, so we have a total of 16. So that's 12 plus 4. Manganese. How many manganese do we have? How many? 1. How many nitrogen? On our product side, how many sodium? 1. How many phosphorus? 4. You guys also see that, right? 4 times 1. Okay, how many oxygens? 17. Are you sure? Okay, because we have 4 times 4, which is 16, plus 3, right? So that's 19. That is correct. 19. Okay, and then the manganese and nitrogen. Okay. Ooh, somebody's coffee is finally kicking in. Okay, so Now what we need to do is find a coefficient that will allow these to be balanced. Okay, now I'll tell you the way that I do it for your girl. You can do anything that you want to do, as long as you get to the final answer at the end. The first thing that I do, I take a look and I try to find the elements that looks like it would be the easiest to sit there and solve. Meaning, for me, meaning that they're only listed in one place over here and they're listed in one place over there. Something like oxygen, which is mentioned here, here, and here, and here, that's a little more complicated, right? So I'll save that one for the last. Like when you guys work on a project, don't you do all of the easy stuff first, right? Get it knocked out of the way, and then you save the hard stuff for the end. Yeah. Because then you're feeling more productive. That's the same thing with balancing a chemical equation. Get the easy stuff first, and save the hard stuff for the end. Okay? So if we're going to do that, where do you think we should start at? Sodium. Okay, because we have one sodium here, and we have 3 sodiums here, and we have 1 sodium here in that spot. Okay, so but they're only listed on one side in both cases. So how can I make it so that we have my reactant side? You said I had 3 sodium. How can I get 3 sodium on the other side? What is the coefficient that I need to put there? I need to put a 3. Okay, so if I put a 3 there, that means now I have 3 sodium. How many nitrogens do I have? 3. How many oxygens do I have? Okay, let's do 4 times 4. 16. Plus 3 times 3. 3 times 3? 9. So that's 25. So we have 25. Okay? Good, bad, or ugly? Or good? Is everything balanced? No. So we still got to keep going, right? Okay, so what do you think is next? So at least we got sodium, or somewhat done, but we believe it to be done. Manganese. What was that? Manganese? Manganese? Yeah, I guess we can do manganese. Okay, so if we do manganese, we have 3 here and 1 there. Why not do phosphorus? I'm just curious. Because isn't that next down the line? Yeah, would it make sense to try to do that one? Okay. So let's do phosphorus. Okay, what can I put in front of here so that I would end up with 4 phosphorus? What can I multiply by that 1 to get 4? 4. Okay, so then here I have 4 phosphorus, but that's going to change my sodium, right? How many sodiums do I have now? We have 4 times 3. 12. Okay, how many oxygens do I have now? We have 4 times 4. 16 plus, then over here we have 4 times 3. 12. 16 plus 12 is 28. Okay. So our phosphorus are good. So now we probably should go back to our sodium, since we know that that one didn't quite work out the way we thought it did. Okay. So what do I need to put in front of it? We had a 3 at first. So what do we really need to put in front of it? 12. So I'm gonna put a 12 here. Okay, so that changed things a little bit. Now, we got the 12, 12. How many nitrogens do we have now? Nitrogens here. 12. And then how many oxygens? 12 times 3? Plus, we had 4 times 4. We had 36 plus 16. Thirty-six plus 16, 52. That is a lot of oxygen. So we have a total of 52 oxygens. Okay, so sodiums are good, phosphorus are good. These guys aren't. So we need to get our oxygens, our magnesiums, our manganese, and our nitrogens correct. So, what do you guys think? Should we start off with? We should still save oxygen for last because it's a hot mess, right? So, if I want to get my manganese correct, what do you guys think we need to multiply? 3. So, I'm going to put a 3 here. So then that will give me a total of 3 manganese. How many nitrogens do I have now? So right here we got 4 times 1, and then times 3. So what is 4 times 1? 4, and then times 3, 12. Okay, so then how many oxygens do I have? So we have 4 times 3 times 3. So 12 times 3, 36. And then over here we have 4 times 4. That's a total of we have 52. Okay, so we have 12 and 12, 4 and 4, 52 and 52, 3 and 3, 12 and 12. Okay? Is it balanced? That's it. Okay, so that was a harder one, right? So you'll probably see something like that on at least one of your questions. Okay? So let me show you the easier way of doing it, right? Because that seemed a little bit hard, right? We have to go through it a couple of times to get it to work out, right? Okay. So let me show you it's a quicker way. I say necessarily say easy. Everybody got this down? So I'm gonna erase everything except the chemical formula. Okay. So if we take a look at this chemical equation, right, we'll notice a couple of things. If you look at it from far away, you'll notice a couple of things. We have this PO4, right? It's over here on my reactant side, but we also have on my product side that PO4. So do you guys see it right here? Have you ever guys played with Legos? Anybody play with Legos? Okay. So if you look at Legos, don't we have ones that have like 4 prongs and they'll be a different color, right? And so that'll represent something for us, right? With that 4 prong that's yellow, and then we'll have a 4 prong that's blue, right? So this is like that unit of that four prong, right? It's moving as a unit, okay? So then I can write this as a unit. So I'm gonna write my sodium by itself. And then I'm gonna write PO4. And then I'm gonna do the same thing with the manganese, just my Mn. And then I'm gonna write it as NO3. Now I'm making this a unit because it's moving like a unit. Okay? So then if I go through, how many sodiums do I have on my reactant side? 3. I have how many PO4s here? 1. Right? I have how many Mn here? Manganese. I have 1. And then here's the beauty of it, because if there's multiple of these polyatomic ions, we put them in parentheses, we put the number on the outside. That number on the outside tells me how many I have. So how many nitrates do I have, which is NO3? What's his number? 4, right? Okay, now we go to the other side. How many Mn do I have? 3, because the subscript is right next to the element that we're talking about. Mn, 3, right? Now this is acting as a unit. How many PO4s do I have? That's right. And then sodium. How many sodiums do I have? And then how many NO3s do I have? I have 1, right? Because there's no parentheses around it, right? And it's all by itself. So I only have 1. Does that make sense? No acknowledgement? Okay. So, is it balanced? Okay. So then let's start with our sodium. We can start with the same mistake that we did. Let's not start with sodium. Okay. Let's start with our phosphate. So I have 4 here, I have 1 here. So what has to go in front of this compound? 4. So then that gives me 4 of these. How many sodiums do I have now? 12. Because we have 4 times 3 is 12. Okay, my Mn. I have 3 over here, and I have 1 over here. So what has to come go in front of here? And then that means how many NO3s do I have? Right now we have, see, that's 4 times 3. Okay, it's looking pretty good. So I have 12 sodiums over here, and I have 1. So what do I need to put in front of that sodium? And then how many NO3s do I have now? 12. Questions? Yes.
Is that only for elements that are together?
Yeah, so if they're moving together, they're moving as units, this works out. That's only if they're moving as units, because then you can put them as a unit. If they're not moving as unit, you gotta have them separate. Okay? Because here, This told me I had 3. On the other side, this here, it's understood to have 1, right? I need to have 3 because I have 3 over here, right? So to balance that out, I have to have a coefficient of 3. Because this is my chemical compound. This always has to stay the same. You can't change it, right? But what we can change the coefficients in front of them to make them balance out. Does that make sense? You're having that look. Okay? So I think we have to do one more to make sure that you guys have a good understanding. You want to do a hard one or you want to do it easy? Do you want to feel good about yourself or do you want to make sure you're learning it? Okay, good. Everybody got this down? Okay, so let's do it the units. Can we do it units? As in groups. Okay, so what would be my elements that I'm going to be writing down? So we have hydrogen, I heard some oxygen, aluminum, and then if I wanted to do it a unit, because I know that I have at least 1 unit that's traveling, right? Or I can just break it up into the elements, either way. Where we have only single elements. Either way will work. Okay? So, on my reactant side, how many hydrogens do I have? How many? 2, you said? Okay.
Why'd you do that?
You mean sulfur?
Oh,
So, because this here is a unit, right? It's moving together. You see it here, and don't you see it over here? Right? So it's moving as a unit. So then I can use it as a unit to keep track of it. Okay? Okay, now since I'm able to use this as a unit, then I have 2 hydrogens here. On the other side, how many hydrogens do I have? 2. Okay, oxygens. We're talking about just the oxygen by itself, not sulfur and oxygen. Okay, so if I look at just oxygen by itself, it has to be alone. It can't be sulfur and the oxygen CO4. So how many of those do I have? And then on the other side, okay, aluminum. How many aluminum do I have on my reactant side? And how many do I have on my product side? Okay, and then the sulfur, the sulfate, the SO4. The SO4, how many do I have on my reactant side? And then on my product side. Remember, it's in parentheses, we just use the number on the outside. Okay, you guys see that? Okay, so if I'm doing it that way, is it balanced? No, it's not balanced. So what do I need to do to balance it? On the reactant side. Okay, so you said on the reactant side, put a 3 here. Okay, so then that would give me 3 here. That will give me how many hydrogens? 6. Okay, is that balanced? No? Okay, so then what do I need to do? For the water, in front of the water, H2O, so 3 here. So then that's how many hydrogens? 3 times 2, 6. And then oxygens, 3 times 1, 3. Is that balanced? Yes. See how much faster that was compared to? Okay, so again, if it's moving as a unit, we can list it as a unit. And it'll make it a little bit easier for us because then all we're looking at is the outside of the parentheses to give me the number that we have. Okay? Any questions? Yes.
Why is it a balloon, not a balloon with a subscript of 2?
It's Al2 and it's Al2 because the chemical formula has to be balanced a certain way. In other words, it always has to add up. This is called what? First,
No, why is it only Al by itself on the bottom?
because we don't put it as Al2 because we want the quantity of the aluminum,
Oh,
right? The only time that you want to put it is, I guess it was moving as a unit, we could have put Al2, right? That would have been fine. And then we would know there's just one of those and one of those. But ultimately, you want the quantity of everything that you have. And so since it wasn't in parentheses, we don't think of it as independent. But I understand what you're saying. It would have worked out the same way because you would have had 1 and 1 on both sides, right? Any other questions? No other questions? Are you feeling confident? So we're gonna move forward. Okay, so the key thing was about this figure is that it is a chemical reaction, right? So we go from one form to another form. So we're breaking down that sucrose to carbon and water. So we know that that is a chemical reaction. So an easy way of defining a chemical reaction is when we have a reaction where we don't get back the same products that we start off, or we can't get back what we start off. So is there any way that I can change my carbon and water back to sugar? Can I just do magic and say, they're gonna be white and crystalline, right? I can't do that, right? So I know that that's gonna make it a chemical reaction. Okay? Now, if I had ice, right? And then I put it in a pot, I boil it, so it's all steam, but I keep that pot completely sealed. Is there any way that I can make that back into ice? I can. So that would be a physical reaction. Okay? So chemical reactions or a chemical change is one thing, and we also have physical change is another. And we have properties that are going to be associated with both of those. Okay? So I want you guys to use your incredible thinking skills. And tell me, the very first scenario, we have a little bonfire going on, right? It's a log that's in a fire. Just toss that log in that fire, it's burning. So, is that a chemical reaction or is that a physical reaction? You write it on paper and then we'll go to a vote. The second scenario, we have icicles and they're slowly melting, starting to get warm. The third scenario, we just cracked open our glow sticks after a wave. Right? So that glow stick cracking and glowing, is that a chemical reaction or is that a physical reaction? Okay, put your answers down on a piece of paper, then we'll discuss them. Now remember, everybody votes. Very first one. A, the log burning. the log burning. Is that a chemical reaction? Those who think it's a chemical reaction, raise your hand. Is it a physical reaction? Raise your hand. Okay, so let's think about it. After that log is burnt, can I collect all that ash and make it into a log again? So that means it's a chemical reaction, right? Okay, the glacier melting, or the icicles melting, is that a chemical reaction? Raise your hand. Or is that a physical reaction? Raise your hand. Okay, we know that that is a physical reaction because we can take that water and freeze it back, right, after it melts. The last one, the glow stick glowing after you crack it. Is that a chemical reaction? Raise your hand. Or is that a physical reaction? Raise your hand. Okay, so we know that that is a chemical reaction because we break that glow stick, it glows, and then eventually it stops glowing, right? Okay, so the next thing that we want to talk about is pure and mixtures. Pure substances. When we make reference to pure substances, a pure substance can be a compound, like sugar, or it could be a single substance like sodium, right? So when we make reference to pure, we're just saying that everything in that substance is exactly the same. It's unique, okay? One kind, okay? So when we make reference to a pure substance, we have pure sugar, pure salt, pure sodium, pure cocaine, pure wax, you know? It means that it's all exactly the same. Now, when we start getting into mixtures, there are two or more pure substances that are combined. Okay, so if I say rum and cola, Coca-Cola, rum, it's actually a couple mixtures because that Coke has sugar, it has coloring, it has a lot of different things in there. Okay, but we know that that would be a mixture. If I said ethanol and water, right, that would be a mixture. If I said salt and pepper, put them together, that would be a mixture. Right? Okay? Are you guys getting it? You seeing it? You feeling it? Okay? So when we talk about mixtures, there are two types of mixtures. We have what we call homogeneous or homogeneous. Right? You also have you heard of homogeneous milk? It's right in the label, homogeneous milk. Homogeneous milk means basically it looks exactly the same throughout. So when milk isn't spoiled, doesn't it just all look nice and evenly white? As soon as it becomes spoiled, does it look homogeneous? No, it's kind of clunky, and then you got a little bit of white, clear stuff, and then a little bit of regular milk looking, right? It looks like a total mixture, right? A clearly defined mixture. In that case, when it's that clunky and the white and all that stuff and the clear all mixed together, you can see all of the different layers, right? We know that that is an example of a heterogeneous. So homogeneous and heterogeneous. Another way of thinking about it is that those roots, homo, when we talk about, like, say, a homosexual. So in that context, that's somebody who is, they like who? Same sex. So same, right? So that root, homo, means the same. So we're saying it looks the same when we say homogeneous. When we say hetero, that means different. So if a heterosexual, they like different sexes, right? So then that root, hetero, basically means different. Okay? So when we talk about solutions, when we're making reference to a solution, we know that that is a form of a mixture, right? When we make reference to a solution, it's a form of a mixture. When we make reference to a liquid, it can be a mixture or it can be pure, right? So, I got carried away. There we go. How many of you guys cook? Anybody cook? Yeah, you guys cook pasta, spaghetti. Why do you guys add salt to the water? What was that? So you get flavor, okay. And I heard over here, it does what? To help boil it? How does it help boil it? Can you elaborate? Teach me something. If I say you're wrong, I believe you're right. I just need, you don't know what I'm saying? Okay, to make it boil, okay. So we add salt to make it boil. Okay, we got, we'll preach to that. Anybody else wanna give me insight, teach me something? It gets colder, so it has something to do with keeping or messing with the melting temperature. That you're saying? So like if you're making ice cream, you put, they call it rock salt. You put rock salt on the ice to help keep that ice cream going, so your salt doesn't melt as fast, right? Okay. So now what you guys are suggesting, yes, it does, it helps with that boiling, and it also helps with controlling that temperature, right? So what it does, the addition of salt is playing a part in the case of the boiling. It allows us to boil at a higher temperature. So normally water boils at 100 degrees Celsius. So if you guys look on my beautiful graph here, you'll see as we increase the temperature, it moves up, and then when water gets to 100 degrees, it starts to boil. And then at boiling point, it stays, the water will stay at boiling point. The liquid, the liquid will stay at 100 degrees, but the gas will sit there and go up, and it can technically be higher than 100 degrees. But the liquid is gonna be at 100 degrees. So if you stick a thermometer in the boiling water, it will be 100 degrees. Now, if we add salt to that water, it allows us to increase the temperature where water would boil. The more salt you add, the higher it's gonna go up, because that salt affects that boiling point, okay? Now, boiling point is considered to be a physical property of water. So, but by us adding salt to our solution, we're affecting that physical attribute of water. It no longer is valid, okay? So, why do we do that? Why do we want to boil at a higher temperature? To cook it all the way through, okay? Yeah, that's it. Speed up the process, yeah, speed up the process. What is the benefit of speeding up the process? If I let it sit too long and I keep my noodles in there a long time, what happens to my noodles? It overcooks and they become what? Soggy. Anybody like soggy noodles? Oh, exactly. Nobody likes soggy noodles. So if you sit there and you put some salt in there and everything, of course there's a benefit. It does add flavor, right? Love me some salt, right? Probably might have high blood pressure. Anyway, you put that in the water, and then we put our noodles in there. Our noodles are gonna sit there and they're gonna cook faster, right? Because it's at a higher temperature, so we don't have to leave them in there as long. They don't get soggy, okay? But if I put them in there when we're just turning it on and it's cold, we have our noodles in there. Then what happens? They start getting soggy out of the part. You'll have uneven cooked noodles because you have the part that's sticking out, and you have the part that's in the water. That part that's in the water is gonna get all nice and soggy. The one that's on at the top is gonna be kind of hard, and you know. And so it's not so good, right? But if we have it all nice and hot water, we throw our noodles in, doesn't have clippers on it. Good job. So if we talk about our solution, right? We talk about those pure substances and this mixture. So we have the first case scenario. We have bromide. Bromide at room temperature is in a liquid form. Bromide at room temperature is in a liquid form. So would that be a pure substance or would that be a mixture? Pure, it also says purine, right? Pure bromide, bromine, sorry, not bromide, bromine, pure bromine. And then the second one, it's water, H2O. Water, pure, okay? Now, if I mix bromine and water, right? Small amount of bromine, large amount of water. Is that a pure substance? Is it a mixture? Is it homogeneous or is it heterogeneous? Look at it. Does it look heterogeneous? Like if you look at the glass, don't look at the molecules, right? So at a molecular level, we know that it's two different mixtures, right? But when we're talking about whether it's homogeneous or homogeneous and heterogeneous, then we're making reference to what we see visually, right? So if you look at the glass, what do you see? Can you tell the difference between the water molecules and the bromine molecules? You can't. So is that homogeneous or is that heterogeneous? I need you guys to say it. Homo, doesn't it look all the same? If it looks all the same, it's homo, right? It's homogeneous, okay? Or homogeneous. What about the next case? If we add more bromine to the water, is it a mixture or is it a pure substance? The mixture. Is it homogeneous or heterogeneous? Is it hetero? Look at it, look at the glass. Doesn't it all look the same? Okay, so we're not talking at the molecular level, right? Because we know that they're different at the molecular level, but we're talking about what we see visually. Because what we're doing, we're going to be able to visualize things. We see things, right? We don't have such high technology in this lab that we can actually look at the individual atoms and see that, well, this is two different atoms. Okay, so let me give you guys some scenarios. I'll tell you what I did when I was a kid. So my family, we would go to Denny's to sit there and celebrate big events. You know, somebody getting a new job or something like that, and we hire a family. And so we'd get a chance to go to Denny's, and that would be pretty much the only time that we'd go out to dinner, was in situations like that. So when I had the opportunity to go out, I noticed that the sugar and the salt looked exactly the same, right? And then when I was a kid, this kind of tells you, dating myself, they used to have the container where it was all sugar in a single glass container, right? And then you have the salt and pepper shakers where instead of giving you guys the packets that we get now, we didn't have the packets then. It's probably because of me, kids like me. So what I did, I would open it up and I would put the salt into the sugar, right? And I close it. And then I'd go and then I'd watch people as they put sugar in their coffee, right? And then so you see a couple of people and they do it and they're like, and then they take a little sip more and like, you know, they're like, something's wrong with my coffee, right? And so I used to get such a chuckle out of it, right? So in that situation, that salt and sugar added together, is that homogeneous or is that heterogeneous? Homogeneous or heterogeneous? It's homogeneous, right? Because do they look different or do they look the same? They look the same. You can't tell the difference between salt and sugar by looking at it, right? Everybody's like, I can't, right? You cannot. I will sit there, I will grind up that salt so it looks just like that sugar, right? You can't tell the difference. Okay, so we've talked about solutions. So a solution is always going to be a mixture. Okay, so when we make reference to a solution, it's going to be a mixture of two or more, right? It can be two or more substances, that could be molecules, they can be ions, but we know that it's two or more things, okay? And we talked about homogeneous or homogeneous or heterogeneous, right? And you see those rules, homo, hetero. Homo meaning same, hetero meaning different, okay? So, and we're making reference to what we see visually, okay? Oops. So, in the first case, we have water. Is that homogeneous? pure. Actually, that's a typo. That's actually not true because we're talking about a pure substance. When we make reference to homogeneous, we're making reference to what we see visually, of course, but we're making reference to a mixture, right? So it's kind of like a step. So we should have a line going through that. It should say pure. Okay? So again, homogeneous makes reference to mixtures. Okay? And that's one of the typos that were in the books. So. Okay, so then the next thing is, if we have pure ethanol, we know it's also pure. Again, it's making reference to it's not making reference to a mixture, but it's making reference to a pure substance. So again, that would be another example where we would just say pure. The last case, when we have water and ethanol, vodka with water, essentially, right? Is that homogeneous or heterogeneous? I said if we have vodka and water, which is just water and ethanol, then is it homogeneous or is it heterogeneous? Homogeneous. Okay. Any questions so far? Now here's the beauty of it, right? If we have mixtures, right? We have two independent substances that are not reacting with each other, like the ethanol and water, right? We can use physical properties or physical characteristics to sit there and separate. So let's talk about ethanol and water, right? So when you're making ethanol, is made with bacteria or yeast. Primarily, yeast is a primary source. So if you're making like whiskey, vodka, and beer and stuff like that, you use yeast. This is their name, right? It goes through a process called fermentation. Now, on the average, a batch of fermentation will give you about, if you're really good, 25% alcohol. That's like if you're trying to just get just pure alcohol, that yeast will give you about 25% alcohol and then it starts dying and then it won't be able to make it more. Right? 25, I think the best is like 28%. Okay. So when you guys go to the store, I know most of you guys are not old enough to drink, right? I'm not gonna mention any names here, but anyway. So have you seen alcohol at higher percentages than 25%? Right? Have you seen it like at 80%, 90%? Right? Have you seen it at 90%?
No.
You ever heard of 151? 151 wild turkey? Yeah. So there's a few of them out there. Yeah. They're horrible. They'll put hair on your chest. Even if you don't want it, Okay. So what was that? 151. So 151 wild turkey. So in those cases, right? How are you getting from that 25% alcohol to 90% alcohol or 80% alcohol? Okay, yeah, it's distillation. Yeah, it's distillation, right? So in a distillation, what it does, you're separating two liquids based upon their boiling points. Alcohol boils at 100 degrees Celsius, and then ethanol, not ethanol, wood alcohol mixed with wine. Ethanol boils at around 80, I think it's like 86.1. And so 86.1, so long as you have it above 86.1, the ethanol is going to boil out where the water, most of the water is going to stay. Okay? And so then you're able to sit there and separate and concentrate the alcohol because you make it into a vapor, then you cool it down and collect that vapor, and then you make it back into a liquid. So you're getting your alcohol and you're getting your water. And you're using physical properties because that boiling point is a physical property of the element, of the compound, of the substances. Okay? I like it when it works. Okay, so if we had a mixture of iron and sulfur, well, we know that iron is magnetic, right? So that basically means that we can sit there and get a magnet and collect it. So if I have this mixture of iron and sulfur, I can actually collect all the iron out of the sulfur by using the magnet. So what are we using in that context? Is that a chemical property or is that a physical property of iron? Oh, you found it, huh?
Oh, I did, but that was.
It is a physical property, that is correct. It is definitely a physical property. Okay, so if you guys, anybody eat cornflakes? Or have eaten cornflakes, right? Cornflakes has a very high percent of iron in it. If you guys actually take cornflakes, crunch them up, right? To like a nice little fine powder, and then you put a magnet over that, you'll actually collect all of the iron out of your cornflakes. Take it back to cornflakes, test it out. I'm joking, don't do that, your parents will probably kill you. Wasting that food, right? Okay, I carried away again. Okay, so we can separate mixtures by physical properties. Distillation, you had mentioned it earlier, right? So we can use distillation to sit there and separate it. So you guys, deionized water. Have you heard of deionized water, right? Deionized water is water where you remove all of the ions, right? One way of doing that is by boiling. You're boiling off just the pure water and you're leaving the ions in solution. Another way is by filtration. You can use a filter. How many of you guys drink coffee? How many of you guys need to drink coffee? Okay. You're like, no, I can't. I go off the wall. Okay, so when we use a filter, you guys make coffee, anybody make it? Or your mom? Where's our cake, by the way? We're still waiting. Okay, so we're gonna use filters to sit there and separate the coffee grinds from the solution, right? Because we know the coffee grinds are gonna be a solid and the solution is gonna be a liquid and it just flows right through. Okay, so that process is called filtration. So you guys know about distillation. Distillation is using what? Yeah, but that's the equipment that you're using. But what are you using? What properties are you using of the two different things that are in the mixture? Or the multiple things that are in the mixture? We're using the boiling point. And then in the case we're trying to separate a solid from a liquid, we can use filtration. Right? So these are some of the apparatuses. This is a laboratory distillation apparatus. So a distiller is essentially like that, but it's typically a bigger scale. So when we're distilling alcohol, it's this big metal drum that you sit there and you use, and you heat it up, and you have these pipes coming down, and you have cool water coming through it. That's exactly what's happening here. You know, exactly the same concept. So at the bottom, you have the distill flask. You put your solution that you need distilled. You have your Bunsen burner. Your Bunsen burner basically heats up your solution. Your solution starts, and you want to be cognizant of how hot it is and everything like that. It forms vapor. The one that has the lower boiling points will boil first, and then it will actually go form a vapor. It goes up, it goes down this tube, and then as it goes down this tube, it gets cooled by running water. So we typically have cool running water to sit there and cool it down. And then we collect our pure substance on this side. Okay, in this case, we have a liquid that has a higher boiling point and water. And then so we're able to collect the water because it has a lower boiling point, so it's going to boil first. Okay. This here is an example of gravitational or gravity filtration. So in this case, we're using filter paper. So this white piece of paper, we're going to fold it up, and then we're going to collect the solid using our filter, right? And so you just put that into a funnel, the paper to a funnel, you put your liquid in there, and then you're able to separate your solids from your liquids. Okay, so we know a pure substance can be elements, or they can be compounds. So elements and compounds. Did we talk about this? Yeah, we did talk about it, we talked at the very beginning. So. Definition of an element is going to be a, let's say, one type of atom only. Definition of a molecule is going to be two or more atoms bonded together. Definition of a compound is going to be two or more different atoms bonded together. Now, all three of these can be pure substances. The element, the molecule, or the compound. All of them can be pure substances. Now, it becomes a mixture if we have two molecules that are coming in together that are not interacting with each other. Right? So it becomes a mixture in that case. Okay, so I'm going to put a couple of things on the board, and I want you to tell me whether or not it's going to be element, a molecule, or a compound. Okay? Okay, so based upon the definition, we have O2, which is for oxygen gas. Now, I talked to you guys about diatomic elements. What are diatomic elements? What are diatomic elements?
Elements combined together.
Okay,
Yeah. Sodium, chloride, chloride, sodium together.
diatomic element. Element, the definition of an element means it has to be only one type of atom only, right? Di means two, right? So let's take a step back. There are, before we finish this, there are 7 diatomic elements. There's hydrogen, there's nitrogen, there's oxygen, there's iodine, there's fluorine, oxygen, iodine, chlorine, and bromine. Okay? Have no fear of ice cold beer. Okay? Okay, so what this means is that these elements, when they're normal conditions, normal room temperature and everything like that, they like to be paired up with themselves. So when we're talking about hydrogen gas, we're making reference to H2. When we're talking about oxygen gas, we're making reference to I2. If you guys look on the slide earlier when we were talking about bromine, liquid, right? Then we know that we're talking about Br2, okay? So these are the ones that are diatomic. Di meaning two, atomic meaning atoms, two atom elements. So in nature, there are two atom elements, okay? So these are your seven. You're responsible for knowing your seven diatomic elements. So when we're writing them in a chemical formula, when we're talking about bromine, right? We know that we're going to write Br2, it's only bromine. Now, let's say we're talking about water, right? Water has hydrogen and oxygen. It's always going to be written as H2O because that is the chemical formula for water. The chemical formula for oxygen gas is O2. It's always O2. Okay? So we only do it when they're all by themselves, all by themselves. Okay? Questions? Any questions? Any concerns? Okay. So now that you guys know that these are diatomic elements, there's also two polyatomic elements. What does poly mean? Poly. No one? Anyone? Poly? Polygon. Polyamorous. Polygamous. This is a great popular. You're dating multiple people. What do they call it? Polygamy is when you're married multiple people. So when you're dating, they call it something else. What was that? I heard that. I heard you say, oh, yes, it's true, but so poly basically means many, right? A polygon, many sides, right? Okay, so polyatomic means polyatomic element. Okay, so we have two polyatomic elements. We have phosphorus, which is P4, and then sulfur, which is S8. Okay, so the preferred form, now these guys are a little bit different. Sulfur, it's like the majority of the time it's going to be S8. Phosphorus has multiple forms. One of them is P4, and one of them is just P. Primarily with P4 when we're talking about phosphorus. Okay, so those are examples of polyatomic elements, where the others were diatomic elements. Okay, questions? Okay, so now let's do a little quiz here, right? Everybody got this part down? I can erase it. Just want to talk about this. Maybe I have a dream about it. Okay, so now I need you guys to talk to me. Okay, you guys ready to talk? Name the 7 diatomic elements. You give me one. No. I don't know. Look at the paper. P4, is that diatomic? H2. Okay.
N2, 0.
And 2.
0 to I2. Br2, and Cl2.
Simple, right? Okay, so now that you guys know that, we know that those are diatomic elements. So we have O2 on the board. Is that an element? Based upon the definition. What is the definition? Only two. One type of atom only. It's not only one, it's just one type, so that means I got multiple of them, right? So, is it an element? And then the name, doesn't it say God, atomic, element? So is it an element? How many of you guys think it's an element? Raise your hand. O2. Okay? Based upon the definition, it's an element, right? It is an element. So we're going to put a check mark here. Okay? So, is it a molecule? Based upon the definition. Read the definition. Yes, because it says 2 or more atoms. Doesn't this mean 2? Yeah. Based upon the definition, is it a compound? No, it's not a compound. Okay, so we know that O2 is going to be an element and it's going to be a molecule, right? It's an element because it's only oxygen. Okay? It's a molecule because there's 2 of them. Okay, what about NO3? Is that an element? No, because it's an N and an O, so it's a no. Imagine that, you know? No? You guys are rough, hard crowd, I see this. Is it a molecule?
Yes.
Yeah, it's a molecule, right? Because the definition says 2 or more. Man, we got 4 there, we're doing really damn good, right? Is it a compound? Okay, so we know it's a compound because it's 2 different. We have an N and an O. Okay? What about AU? AU stole my gold. Gold. Is it an element?
Yes.
Is it a molecule? No, it's not because it's not 2 or more. We only have 1. Good job. Is it a compound? Zinc. Zinc. Is it an element? Yes. Is it a molecule? No. Is it a compound? No. Sodium chloride or salt, is it an element? No. Is it a molecule? Is it a compound? Are you sure? It is. Good job. Just had to give you a hard time because only 3 of you guys are answering. Now I know that there are more than 3 people in this class, so I expect more than 3 answers in this class. Because what is that thing? There's that rule that we gotta do what? What do we gotta do? On the syllabus. Say it again. Say it so they can hear it. Participate, okay? Now you want to make sure you get those points for participating. So you guys need to do what? Participate. Now, is there an issue with being wrong right now in this class? I just want to know. No, there's nothing wrong with being wrong. It's okay to be wrong here, right? Because you want to be right on the test, right? And in real life, you don't want to blow up anybody, right? Right? Okay, that's good. You had me worried there for a minute. You weren't answering. Okay, so we don't want to blow up anybody. So we want to be, it's okay to be wrong in the classroom so we can learn, right? Because we learn more from being wrong than being right. So don't be scared to answer. It's okay. This is a learning environment. It should be a safe environment. It's okay to be wrong. And nobody thinks you're stupid because everybody's the same way. If you notice, you don't have 3 people answering, right? So it's okay to answer. You're going to be wrong some of the time. That's the way you learn. Okay? That's part of learning. Okay, any questions? Any concerns? Anybody want to give me some money? Also cash money. Okay, so if we look at this, mixtures we can separate by physical properties, physical meanings, right? Physical characteristics. So if we have mixtures, which is going to be impure, right? We consider it separate. But if it's pure, a pure substance, right? We can only separate by chemical means, meaning that we can only separate into elements or compounds by chemical means. So in other words, if we're looking at water, and we want to separate water into oxygen and hydrogen, right? We have to do a chemical reaction to make that happen. You can't do it by physical reactions because water, the H2O is bonded together. They're bonded together. So we're going to have to use chemical means to do that separation. Okay, so these are some examples of some of your common elements, right? Gold, silver, lead, copper, silicone. And then on the other side, we have examples of compounds. A lot of these compounds we run into, right? Naturally, baking soda, which is sodium bicarbonate. We have Rolaids, I can't remember what it is, I think that's bismuth something. No, that's Tums, bismuth, that's bismuth something, I can't think of the top of my head. But the point is, or ethanol, we have drinking alcohol, we also have water, right? So all of those are examples of compounds, and compounds that we use, you know, to sit there and relieve our stomachs or to dye our hair or to clean our drains. As I said, dye our hair. Look who turns around. She's like, oh, okay. So you guys are already familiar with the symbols. How to look at the periodic table. We know that capital letter, right? The single capital letter, it means that compound. But we also know that we can have a capital letter and a lowercase letter. So He is for helium. Right? And so you guys know how to read the periodic table and use those symbols to determine what the element is. We know when we talk about the 2 at the bottom, that represents the subscript, so H2. So that lets us know how many of those atoms that we actually have. So we know that we could have multiple element compounds, or multiple element molecules, which we call compounds. So HCl, right? HCl has hydrogen and it has chlorine, but it gets bonded together to form a compound. Okay? H2O, well, we have 2 hydrogens, 1 oxygen. Okay? So if we look at barium chloride has how many barium? 1. How many chlorine? 2. Okay, what did we talk about earlier? Starts with a P. Dissipation. What else? They're gonna be heard later on. So we already talked about the atom, right? We talked about molecules. So, what was that? Is that what I said? So here, there's a law of definite composition. The law of definite composition basically says that when you have a compound made up of different elements, the proportion of that mass is going to always be the same. Okay, so when we have a compound made up of different elements, the proportion of that mass is always going to be the same. That's the reason why we call it the law of definite composition, right? It's composed of those 2 elements, right, or both elements. So the law of constant composition. So what does that mean? Should have a slide there. So let's go. So what it means is, if I have carbon dioxide, and I have carbon monoxide. Okay, now the ratio of carbon to oxygen for carbon dioxide is what? How many carbons do I have in carbon dioxide? And then how many oxygens do I have in carbon dioxide? I need 2 oxygens. Okay, there we go, 2, right? So I have 1 carbon and I have 2 oxygen, right? So if I take the mass of carbon, you guys have your periodic table available. mass of carbon is. Okay, so what we're gonna do, we're gonna calculate what we call is the formula mass or the molecular mass. So we know that it's 12, carbon is 12. We're just gonna do a quick round. And then oxygen is 15.99, can we round it up to 16 and feel comfortable with it? So we're gonna round it up to 16. And then how many oxygens do we have? So we're gonna 16 times 2. You guys mind if I move to the board here? Because it's easier to do it there. What was that? What about the eraser? I need a big eraser. Yeah. Okay, we have CO2. And we have CO. Okay, so we said carbon weighs 12. Oxygen, there's 2 of them, so it's 2 times 16. So we're gonna add that together. So 2 times 16 is what? 32. Plus 12, so that's 44. Now, this is called the formula mass. So if we're talking about just a single formula or molecular mass, right? Formula or molecular. In this case, it's really molecular. So we would use A and U. If we're talking about what we call the molar mass, you guys already know what a mole is, right? What's a mole again? 1 mole is equal to what?
6.0.
Times 10 to the 23rd. That's right. Okay, so we also have the molar mass. The molar mass is what we can work with, right? So then in that case, we would use again 44 grams per mole. Okay? They're comparable to each other. Only thing the formula mass means that we're only working with like 1 molecule, right? The molar mass means that we're working with at least a mole of stuff, right? And they end up being the same. Okay? So this is called the molar mass. And this is called the molecular mass or formula mass. We'll distinguish between that later on, okay? Now, this guy is 44. So if I have 54 tons of carbon dioxide, right? The ratio of the masses are going to be the same. We're always going to end up with that ratio of 12 to 32. Always, because it doesn't matter how many we have or how much we have, it's still going to be carbon dioxide because that's what it's made of. Where if we take a look at carbon monoxide, so we have our carbon. How much does carbon weigh? How much does carbon weigh? 12. Okay, and how much does oxygen weigh? Okay, 12 plus 16. Okay, so we have 28 AMU or 28 grams per mole. Okay, so in this case, we know that it's going to be a 12 to 16 ratio, right, of carbon to oxygen. Okay, so it's always going to be that ratio because the chemical formula isn't going to change. The chemical formula is always the same. So regardless of how much you have, you're always going to end up with the same ratio. That's all I say. Doesn't seem like a big deal, right? Because it makes sense to us, right? But at the time, they were like, man. Okay. Okay, so the other thing that we need to talk about is that positive and negative charges. We know that if we have a positive and a negative charge coming together, what's gonna happen? They're gonna attract, that's right. Positive and negatives are gonna attract. Now, if there are two negatives, what's gonna happen? Two negative people in the same room? Have you ever had two negative people in the same room? You're like, no, you guys gotta get away from each other. You need to go over here, you need to go over there. So if we have two negatives that are coming together, they're gonna repel each other. So like charges repel, different charges, unlike charges, attract. So positive and negative attract. Negative and negative, nope, not gonna work. Positive and positive, nope, not gonna work. Okay, so when we're talking about chemistry, it's really important for us to understand that these are called electrostatic forces. They're based upon charges. They're based upon, we say electrostatic, they're based upon electrons. Electrostatic, right? Either you're gaining electrons or you're going to be losing electrons. Okay? So that's something important for us to remember. So there's this nice little experiment. Well, I don't have all my gear for this. So basically, if you take a look at this, if we take a silk cloth and wipe our little glass rod with the silk cloth, what we're doing, we're going to be, the electrons are going to be transferred from the rod to the cloth. So we're basically removing the electrons from the rod to the cloth. And then if we touch that rod with the little balls, right? And you'll notice that the balls will stick to it, right? So we remove the electrons, so that means that now the rod is positively charged. The pit balls are negatively charged, so they're going to be attracted to it. So we get attraction, right? Now, after we've touched it, right, and if we have the pit balls next to each other, because now each of the pit balls are going to be positively charged because they're going to be pushing each other away, right? Okay, so they're going to be pushing each other away because they're both positively charged. Now, if we do the same thing and we rub it against a little fur, right? A rubber rod against the fur, then in that case, that's going to leave my rod as negative. Those pit balls that were now positive, what is going to happen to it? We have a negative rod, two balls that are positive. What's going to happen if I stick it between them? Let me draw it on the board. Okay, here are my balls, they're positive. And my rod, is negative. What's gonna happen?
Gonna attract to the rod.
Yeah, the balls are gonna move towards the rod. They're gonna be attracted to the rod. Okay? So, opposites are gonna be attracted. So in the other case, where we have the glass rod, where we have this guy was now positive, and then these guys are positive. What happens there? They're gonna repel each other. So we're gonna be moving away from the rod. Okay? Okay, we've already talked about chemical reactions. The right-hand side is called the right-hand side. The right-hand side, yeah, you're right, the product. The left-hand side, I have to look at it. It's called the reactant. Okay. See this? Okay, we've already talked about coefficients. We've talked about coefficients are those numbers that are in front. We've talked about subscripts. Now we can talk a little bit about energy. Energy. So when we talk about energy, energy is defined as the ability to do work or to transfer heat. In chemistry, a lot of it is going to be heat transfer. So we're going to associate energy with heat transfer a lot of the time. The ability to do work, that usually deals with a lot of pressure and volume, and so we will talk about that dramatically. Okay. So the case where we have this very first reaction, right? It's called the burning of butane. So anytime that you have a combustion reaction, carbon and hydrogen reacting with oxygen, you're always going to get carbon dioxide and water, and you're going to get some energy associated with it. So like gasoline, right? When we use gasoline in our car, it's a combustion reaction. We're making energy, right? That's the whole purpose. That's how we power our car, is that energy. Okay, now the thing is that the energy is going to be released. Okay, so it's going to be on the product side. When energy is released, then we call that exothermic, meaning temperature is being released, heat is being released. Okay, exothermic basically means that the reaction is causing energy to be released or heat to be released. Okay, now if it's endothermic, that means that we have to add energy to make that reaction happen. So it's taking energy from the surroundings to make the reaction happen. Okay, that's going to be an endothermic reaction. Okay, kinetic energy. Kinetic energy is the energy associated with movement. Right? So when we talk about kinetic energy, the equation for kinetic energy is going to be so we say KE for kinetic energy. It's going to equal 1/2 mass times velocity squared. Okay. Let's say, I'm having a hard day and everything like that. And then Oscar gets me really worked up, right? Okay. And so, one day I have my ping pong ball and I throw it really hard at Oscar, right? Now, the kinetic energy resulting from that ball hitting me, let's say it's going to be E, right? It doesn't hurt because it's a ping pong ball, right? Next day, Oscar does exactly the same thing and gets me really, really upset. I throw my coffee cup at Oscar, right? At the same speed. Which one is going to have a larger kinetic energy? Which one's going to hurt Oscar more as a result of having a larger kinetic energy? The ping pong ball or the coffee cup? Coffee cup, right? Which one would you rather have thrown at you? Ping pong ball or coffee cup? Ping pong ball, right? Anybody with a coffee cup? No, right? Okay, so why? Why does the coffee cup give us more kinetic energy? Why? If we're at the same speed, what was that? It weighs more, right? So we know that in that case, the kinetic energy, you guys remember we talked about this part. The kinetic energy is it directly proportional or indirectly proportional? Okay, does the kinetic energy go up with mass? Or does it stay the same? which one is gonna have more kinetic energy? Ping pong ball or the coffee cup? Why? It weighs more. Okay, so you're saying mass goes up, right, in that case. So then the kinetic energy also goes up, right? Okay, so is that directly? That's directly, right? So if they're both going up, it's directly proportional. If they're going in opposite directions, it's indirectly, right? That's when they're on the opposite side of the equation, right? Okay? Does that make sense?
Yeah, I think it's not confused.
Yeah. Okay. Okay, so what is exothermic mean? Exothermic? Heat's being released. Okay, so the next part is endothermic, right? What is endothermic? You guys already know this. What's endo? If exo means exiting, right? Exit, right? So it's exiting reaction. So endothermic means what? It's entering, right? It's going in. So we were putting it into the reaction. So we need to put it into the reaction to make it happen. A famous example of this is photosynthesis. We have to get energy from the sun to make it happen, right? And so then that allows us to make sugar, not us, but plants to make sugar and oxygen. Now, the the potential energy is just the energy due to arrangement, location, okay? So let me give you an equation for potential energy. This does not want to work for me today. There we go. So it's the gravitational pull or the gravitational force, which is gravitational pull. It's 9.8. And it would be squared seconds. That's a 2 up top, I'm sorry. There we go. M equals mass. And H equals height. Okay, so in this case, we're saying potential energy. If I have my expo marker up here, I have this height times gravity times the mass of my expo marker is going to give me my potential energy. Right now, it's all potential energy because it's just an number, right? This is the maximum amount of energy that I can have for it, right? As soon as I drop it, that energy is being shifted from potential energy to kinetic energy. So right now, there's all potential, and then there's zero kinetic. Then we're switching it so that we have all kinetic when it hits the ground, it's all kinetic energy, right? And no potential energy. Okay, so energy is conserved. Okay, because we start at potential, and as we move down, kinetic. At the end of the day, the energy that we started out with, we're going to have to end up with, right? Because energy is conserved. So that's the law of conservation, which we're going to be talking about. Can I clear? Everybody got this? Okay. So Einstein basically had looked at energy and converted energy in terms of mass, and that's what we basically did. Only thing, Einstein says that E equals mc squared, where E represents energy. In this case, it would be kinetic energy. But we're making reference to light, and this is making reference to only light. E equals mass, the mass of light, times c squared, the speed of light, okay, which is equivalent to our velocity. So you'll notice that our equation is 1/2 mass times velocity. We use v instead of the speed of light, okay? Now, units for energy, that's going to be joules. It's going to be calories, okay? In the US, we typically use calories. Now, when we make reference to calories, there are two types of calories. We have the small c calorie, and we have a big C calorie. Small c calorie is the chemical calorie, okay? Big C calorie is the food calorie, okay? Now, how do they differ from each other? Well, the small c calorie, 1,000 of the small c calorie will equal 1 big C calorie. I'll write that on the board here in a minute. Okay. Okay. I'll show you everybody here in a second too. The other thing that I want to say is the joule. So the joule is defined as the force of 1 Newton applied over a distance meter. Okay. So. Okay. So for SI units, we use the joule. Now, if it's a force of 1 meter divided by over the distance of, the force of 1 Newton divided by the distance. So it's force divided by distance, and that's going to be equal to energy. Okay, so the units for a joule is going to be or the equivalent, a joule is going to be equal to 1 joule. It's going to be equal to 1 kilogram per meter squared over second squared. Okay, so okay, so when we talk about the joule, we're making reference to the force that's being applied over a distance. So in other words, that's going to be the energy. So the amount of energy I push this table across the room, right? This is going to be the force that I'm applying, and then the distance measured, how far across it, and you can tell how much energy I use to push it, right? So that's the way that we think about energy, right? It's work being done. Because that's work. Me pushing this table across the room is work. Okay? So when we think about that energy, it's force over distance. Okay? But another way of looking at it is when we look at the calories. That's the amount of energy it takes. Let me go back to my other screen. Okay, that's the amount of energy it takes to raise the temperature 1 degree for 1 gram of water. Okay, So the energy it takes to raise the temperature 1 degree for 1 gram of water. Now, that's gonna be a calorie. One calorie is going to be equal to 4.184 joules. Okay? And so that's going to be our conversion. Okay, that's going to be the conversion, how we convert from, because we use joules for SI units, that's the one that we use in science. Calorie is what we use in the US. And so we could have kilojoules or kilocalories. And those are the abbreviations for kilojoules and kilocalories. And then 1 food calorie is going to be equal to 1,000 calories. Or we could say it's equal to 1 kilocalorie. Okay, and you guys got that on the board earlier, right? So if you guys could do me a favor, I want you guys to convert 42.5 kilojoules to kilocalories, to calories, and then to joules. And then for kicks and giggles, also convert it to a food calorie. 1, convert it to food calorie. Okay, so we are starting off with 42.5 kilojoules of energy. So we want to convert that to, first case, we want to convert it to kilocalories. So we want to convert it to kilocalories. That's what we're shooting for. So what conversion do we know that's given to you in the paper that can convert kilocalories from kilojoules to kilocalories? You guys have anything on your paper that says kilocalories to kilojoules?
1 kilocalorie equals 4.184.
Okay, 1 kilocalorie is going to be equal to 4.184 joules, right? Which is the same thing as a calorie to a joule. Since we have kilo, right? Since we have kilo in front, the abbreviation kilo, they cancel each other out. They mean exactly the same thing. So they're going to be equivalent to each other, right? So if I have milli, right? So millicalorie and a millijoule, then we're going to use that same ratio. That's 1 to 4.184. Okay? So this works for any type of unit. If you have those units comparable to each other, they have the same prefixes, it's going to be exactly the same if we move up to different units. So what I'm saying is, that 1 millicalorie, that's going to be the same thing as having 4.184 millijoules, because these are the exact same prefixes. Okay, one of the benefits of using a metric system. Okay, so in this case, I can plug it in. So if I'm trying to get rid of kilojoules, what needs to be on the bottom? Kilojoules. So I'm going to put my 4.184 kilojoules on the bottom. And then I'm going to put my 1 kilocalorie on top. So who's going to do that heavy lifting for me?
10.15.
10.15. You guys agree with it? Anybody who don't disagree with it? Anybody's going to take a risk and not agree with it? How many sig figs should I have? Am I gonna round it up? This is exactly 5. Or is there a number after? Is there a number after the 10.15? 10.157? Oh. There's so many different things wrong with just giving me 10.15, right? So, how many sig figs should I have? I should have 3, because we know that this is a conversion, it's not going to factor into our symmetric figures. But these are, that's 1, 2, 3. So my answer should have 3 sig figs. So what should be the answer? 10.2. Okay, so now we got in kilocalories, right? how can I convert my kilocalories into calories? Kilo, what does that mean? Kilo, what does that mean? What does that abbreviation mean to us? Does that mean 1,000 times greater than whatever unit we're working with? So we know that 1,000 calories is going to be equal to 1 kilocalorie. Okay, so I can actually use this, that 10.2 kcals. I'm not putting 1,000 on the top or on the bottom. 1,000 calories, am I putting it on the top or on the bottom? On the top. So it's 1,000 calories to 1 kilocalorie. Then my kilos are going to cancel out, and I'm going to end up with what should be my answer. I can also, if I wanted the food calories, so I told you I want food calories, which is capital C calories, I can use this because I know that 1 capital C calorie is also going to be equal to 1 kilocalorie. So then, if I was talking about food calories, 10.2 capital C calories. And then if I wanted to change to joules, I know that kilo again, joules. So for every 1 kJ, that's going to be equal to how many joules? 1,000. So then, in that case, okay, questions, concerns? Everybody got it down? Give me a second. Any questions? No questions? Everybody's good? Okay. I like that. Okay. So if we think about when water boils, right? Or when water evaporates, what's happening in the case of water evaporating is that at that surface, water molecules are being released from the water, right? And so they're going into the vapor phase. So you got things that are in the liquid phase that are moving to the vapor phase. And that's being shown here in this slide, right? Can you guys see that? You guys see those water molecules shooting up? Let's see. Right here, right? So water molecules are being released. Okay. Now, the water molecules on top of the water is called water vapor. And this number is going to be fairly consistent. So what's going to happen is that you're going to have ones that are in the vapor that are going back into the water. And then that's going to be at the same rate as the ones that are going to the vapor phase. And so they're going to remain a proportionality. They're going to try to keep that same number. So as one gets away, somebody else gets caught. As one gets away, somebody else gets caught. As one gets away, somebody else gets caught. Okay? So, but that's happening at the same rate. Okay? So when we talk about vaporization or that evaporation, right? We have energy that's going to be associated with that. That energy we call the heat of vaporization. And the way that that's defined is it's just the amount of energy that's required to change 1 mole of liquid to vapor at a constant temperature and pressure. So you're maintaining a constant temperature and you're maintaining a constant pressure. You're just changing 1 mole of liquid to vapor. That's how much energy it takes to do that. Okay, now this is going to be dependent, or it's going to be part of it's going to be that boiling point. The boiling point is just a point where the vapor pressure becomes equal to the pressure that is above the liquid. So the temperature where vapor pressure becomes equal to the pressure that's above liquid pressure. And so that's where we get that boiling at, right? So if we look at this, as we're moving from liquid to vapor, that's called the heat of vaporization. And so that's an endothermic reaction because we have to put energy in to make that happen, right? To change liquid to vapor, we're putting energy in, okay? Now, if we go back from vapor to liquid, that's called the heat of condensation. That's an exothermic reaction. That basically means that energy has to be released to sit there and to go from that stage. Okay, so when we're boiling, what's happening is that here we have those gas bubbles, right? They're trying to escape and they're working their way through the water. So, and that's what you're seeing up here. So inside we have those gas bubbles that are forming, they're trying to escape and then eventually they get to the surface and then they're free. Right? Where down here, this is all liquid, they're gonna be tight together. So if we look at this, we have this equation. Q represents the amount of heat, or we call it the energy. It's going to be that case of the energy. So Q is going to be equal to the heat of vaporization times mass. Okay? Q is going to be equal to the heat of vaporization times mass, or it could be the number of moles, depending on how the heat of vaporization is shown. If the heat of vaporization is in joules per mole, then we're going to use moles. If the heat of vaporization is in joules per grams, then we're going to be using grams. Okay, so there's 2 ways of showing the heat of vaporization. It could be either energy, which is joules per moles, or joules per gram. So the units. So delta H units are going to either be joules per mole or joules per gram. Okay, they could also be calories per mole or per gram, but in any form, it's gonna be energy over quantity or energy over mass. So depending on what our delta H is. So when we make reference to the heat of vaporization, we call it delta HV or delta HV. And then if we make reference to the heat of condensation, it's going to be delta H con, right? The thing is that the heat of vaporization is going to be in one direction, and then the heat of condensation is going to be opposite. So they're going to be the same value, but they're going to be, one is going to be positive and one is going to be negative. Here are some examples. So we have the heat of vaporization, and fusion is the concept of going from liquid to a solid. Sorry, from a solid to a liquid. So basically melting is what we call fusion. Okay, heat of vaporization is going from a liquid to a gas, right? So these are the values. If you take a look at the top, the units are kilojoules per gram. So in this case, we're using mass, so it's energy over mass. And then in the case of fusion, is joules per gram. Okay, these are going to give us our melting points and our boiling points because those are going to be relevant for us to understand things. Okay, and I think I'm gonna have to stop here before we get into the event. We got 5 minutes left. I think this is a good stop.